This is Science Max, Experiments at Large. Science Max! This episode of Science Max Experiments at Large is all about light. And bending light to your will. Right? And challenges me to an ever more tricky game of light manipulation. Plus lasers, periscopes, and what does that have to do with light?
Cut to animation!
Find out on Science Max Experiments at Large. Greetings, Science Maximites. I'm Phil, and today on Science Max Experiments at Large, we're going to be looking at light. Okay. Just stay. That wasn't supposed to happen. I was supposed to press that button, and there was supposed to be all these lasers and special effects, but it didn't. Well, today on Science Max Experiments at Large, we're not going to be doing one experiment. We're going to be doing a number of small experiments because we are going to do a light manipulation challenge. I'm going to get an expert, and she's going to challenge me to a game of light manipulation because I am the master of light. Oh, well, at least the green lights are working. And okay, forget it. I'm just gonna turn it back to normal. Come on, back it. I'm gonna work on that later. I'm gonna need an expert to help me though. Oh, I know, Anne would be really good at this. It really does look kind of weird in here, doesn't it? Oh, well.
You okay?
Hi.
Hi,
Anne.
Phil.
Yeah, I couldn't see what I was doing. Here's your lab coat.
Oh.
Thank you for coming.
Great.
Now, you're from Let's Talk Science, right?
Yes, that's right.
All about science education, just like us. Now, you're gonna challenge me to a light manipulation game?
A light manipulation game. I've been working on a series of challenges since last time we talked. Each
Awesome.
a little more difficult than the last.
Well, this is gonna be great, because I am the light manipulation master.
Okay, well, we'll see about that.
Okay. Challenge number 1.
Take a seat.
Oh, that's easy enough.
I have written something on the back side of this ball.
Okay.
And I'm gonna challenge you to read it.
Okay, well, I'm ready. I might be able to read it from here. Let's see.
All right.
Okay, I see something's written on it, but I can't read what it says.
What if you squint?
It looks like a couple lines, maybe? I can't quite tell.
Any ideas how to solve this challenge, Phil?
And I have to be in this chair?
Well, you can get out of the chair to set up your solution. But
Okay.
when you read what I've written on the ball, you have to be sitting in the chair.
Well, it's light manipulation, right?
Mm-hmm.
So, wait a minute, I've got flashlights in case the power goes out, so maybe I can use a flashlight. Haha, okay, ready? Pew! Doesn't seem to make it any easier to read. Yeah, I got nothing.
Did you give up already?
No, of course I don't give up.
I told you these were gonna be challenging.
This is nothing. I will figure this out. I don't know yet.
You're gonna have to get creative.
I don't know yet, but I will think of something.
Okay.
Okay, I will be back. Here, hold the flashlight. Not looking. I'm gonna go this way.
I'm gonna wait right here.
Okay. Have you ever wondered why you end up upside down when you look at yourself in a spoon? It's because of light reflection. Light is made of photons. Let's say that these tennis balls bouncing off this wall are photons of light. Now, when the surface is flat, like a mirror, the photons, they bounce in and straight back out again. But when the surface is curved, the photons don't go straight out, they get reflected. So now, this photon is going over there, and if we had photons on this side, they would go. I don't even know where those ones are coming from. Then, okay, so we got photons on this side that are going that way, and photons on that side that are going this way. So the top becomes the bottom, and the bottom becomes the top, and that's why you look upside down when you look at yourself in a spoon. Okay, cut to animation, cut to animation! A lens works by changing the direction of light, too. Lenses are made out of curved pieces of glass. When the photons of light pass through the glass, the curved surface makes their paths change.
What was only this big before becomes this big when you see it. Lenses are used in microscopes to see things that are really small, or in telescopes to see things that are very far away. Both times they are making something small appear large. Anne has challenged me to figure out how to see a small object far away, and using a lens is my solution.
Check it out. It's a giant magnifying lens, and I'm gonna use it to magnify the ball so that I can see it.
Sounds great.
All right.
I set the lens in front of the ball, which Anne has turned so I can't see what's on it. I add a light.
Shine it on the ball so that it's a little bit better illuminated.
And then sit in the chair and ask Anne to move it so it's aligned.
All right, so bring it to your left. Yeah, keep going, keep going. Keep going, right about there. Try bringing it closer to the ball. Okay, wait, that makes it smaller. Try bring the lens away from the ball. Ooh, wait. Try a little bit further. Ooh, ho, ho, ho.
You're ready for me to spin the ball around?
Yep.
Okay.
It says 71.
Nicely done.
Easy, solved.
Wait.
What?
That was just the warm-up.
Oh yeah?
Yep. You ready for challenge number 2?
Challenge number 2!
I've got another ball.
Okay.
With something else written on it.
Wait, are you coming back?
Nope.
Huh, but I can't even see you from here. Like how am I, huh?
You're gonna have to manipulate the light.
I have to see around a corner? I have to see around a corner. All right, I'll think of something. So you remember the tennis balls in the wall, right? Right? Okay, so the tennis balls are photons, what light is made out of, and the wall is a mirror. Now, right now, the photons are hitting the mirror and bouncing directly back. But what happens if they come in at an angle? Like this. Aha! Those photons are reflecting off the mirror and going that way, which means if I want to see what's emitting those photons, I can see it from here. The same thing happens when you look in a mirror. Oh, okay, mirror. Whoa. The mirror reflects the photons over here. I can see the tennis ball launcher in the mirror, which means if there was a barrier, between me and the tennis ball launcher, I can still use a mirror, and the photons would reflect off the mirror and it comes straight to me, which is how you can use a mirror to see around a corner. In fact, periscopes work the same way. Let's make a periscope right now. Hey, it's dark in here. Oh, right, because I'm gonna show you my laser. So the light from my laser bounces off this mirror in a straight line. Haha, reflection. We can use the power of reflection to make the light go where we want it to. We're gonna build a periscope.
Submarines use periscopes because it's hard to see when you're underwater. A submarine will extend a periscope up above the water. The image up here gets transmitted down here. So someone looking through the periscope underwater can see what's going on up on the surface.
And here's what you need to build it. 2 cartons of milk, 2 small hand mirrors, scissors or a craft knife, a pencil, and science tape, which is the same as regular tape, except you use it for science. And remember, if I go too fast, you can always find these instructions on our website. Step 1, cut the tops off your milk cartons.
Take your mirror and trace out a rectangle as wide as the mirror, then cut it out. Put some science tape on your mirror and stick it in the carton at an angle. Then put a piece of tape on the inside. Then,
Get the other milk carton and do the same thing. Put a mirror on the inside and then stack the milk cartons together. But don't stack them with the holes on the same side. Make sure you stack them with the holes on opposite sides. And here is what's going on inside. You've got your 2 mirrors, and one is angled like that, and the other one is angled like this. Light from what you're looking at comes in, hits that first mirror, goes down to that second mirror, and goes to your eye. You can use it to spy on people from below the table. Or from around corners. So there you go, your very own periscope using light reflection. Did you know that your TV remote can be a flashlight? It's true. If you have the kind of TV remote with a little bulb on the end of it, then when you press the buttons, the bulb lights up. Yeah, I know what you're thinking. You're thinking, Phil, wait a minute, the bulb did not light up, and I've never seen the bulb on my TV remote light up when I press the buttons. Well, that's because your TV remote works on infrared, which is a kind of light you can't see, but you might be able to see it with a camera. If you have a digital camera or a camera on your phone, now you can see, It lights up. And because infrared light works the same way as visible light in that it will bounce off a mirror, here's an experiment you can do at home. Bounce the light off your TV remote off a mirror and turn on and off your television. Check this out. You get a mirror, set it up just right, and then aim the remote at the mirror and it turns off the television. Pretty cool, right? But now, let's max it out. I've got a complex series of mirrors set up here, and I'm gonna bounce the light from the remote all over the room. And here's what that pattern looks like.
The light from the remote hits this mirror, which reflects to this mirror, which reflects to this mirror, and then this mirror, and then this mirror, and then finally to the television.
Isn't that cool? There you go. Maxed out remote light bouncing infrared flashlight. I gotta come up with a better name, but still, it's pretty cool. Oh, all right. Turn off the television and leave the room.
I solved Anne's first light challenge, seeing something far away, with a lens.
It says 71!
But now she's moved the ball around a corner, and now I have the solution.
Mirror! A mirror will let me see around the corner.
Clever.
Right? Okay, so all I gotta do is put the mirror in a position sort of like that, I guess, and then I'm gonna sit in the chair. If you could help me adjust that mirror. Keep going that way. Keep going, keep going. Yeah, stop. Nice, okay. Go ahead and flip the ball around and I will read the message. It is too small. I can't, okay, I've solved this problem though. Okay, flip it around. The lens, I need the lens. So we'll use a mirror and the lens to, good. Yeah, okay. I'm gonna sit in the chair. Here in the chair. It is backwards. Oh yeah, a mirror inverts the image, doesn't it? Mm-hmm. That's okay, I can solve this. All I need, whoa! Other mirror is all I need to solve this problem. So if I take this mirror and I put it here, let's see, there it is. It says 42.
Nicely done.
I am
done?
ready for anything. What do you got planned for the hardest challenge?
Are you sure you're ready for this?
Totally.
Challenge number 3.
Challenge number 3 starts now.
What? Wait. No. This is a light challenge. How am I supposed to do a light challenge if it's dark?
You have to get creative.
But it's dark. Well, okay, no problem. I will think of something. I will be back.
Okay.
Okay, careful.
I'll be waiting. Careful.
So you already know about reflection, right? That's when the beam of light, say from my laser, reflects off this mirror and bounces in a straight line. But check this out. If I don't use the mirror and I shine the laser against the underside of the water, it also reflects, just like a mirror. This is called internal reflection. If I have a stream of water and I put my laser beam into the stream, you can see that the laser bounces around inside the stream of water. It's being internally reflected, and the laser isn't going straight anymore. It's following the stream of water down where the water goes. Internal reflection. Now I know what you're thinking. You're thinking, Phil, how does this affect me in my everyday life? Internal reflection, who cares? Well, I can tell you why you should care in 2 words. Fiber optic wires. 3 words, fiber optic wires. You see, fiber optics carry information all over the planet. The internet, maybe even your television, travels through fiber optic wires. The good thing is, because of internal reflection, you can bend fiber optic wires any which way or around corners, and the beams of light continue to go straight down inside the wires and get out the other end, making it go where you want it to go. Internal reflection, science.
Back to our light challenge. I've seen something small from far away, seen around corners, but now Anne has turned off the lights. But I have a solution.
Ann? Ann?
Careful.
Okay. Sorry, I forgot how dark it was in here. Okay, I figured it out.
Okay.
I have a flashlight.
No.
So all I need to do...
No. Hold on.
What?
There's one more rule I didn't tell you.
What's the rule?
You can't use visible light.
How in the world am I gonna do this if I can't use visible light?
It's a challenge.
Wait a minute. Okay, here, hold my flashlight for a second. I'm gonna make a phone call.
Okay.
I think I know what to do. I'll be back. I'll be
Okay.
back.
Oh, careful. Oh.
Oh, hey, good to see you. Speaking of seeing things, let's talk about the rainbow. All the colors of the spectrum organized in a beautiful pattern. But what are the different colors? I mean, what makes them different? Well, it all has to do with the electromagnetic spectrum. This is visible light. All the colors of the rainbow. And take a look at that little black line that goes up and down there. That's the frequency of the light. Light is a wave. You see the wavelength is a little wider out here on the red side, and it's a little closer together here on the violet side? That's because every color of light has a different length of wave or wavelength. And that is what makes them different when we look at them. But if you think that's all there is to the electromagnetic spectrum, then you're mistaken. So what happens over here on the red side? Does it keep going? Yeah, it does. What? Look, we got infrared here, and then we got microwaves. These are the same kind of waves you use in your oven. And then we got radio waves, which are the same kind of waves you use in your radio. They're all part of the same thing as visible light, huh? Let's take a look at the other end. Remember these short wavelengths over here beside violet? Well, does that keep going? Yeah, if they keep getting shorter, you get ultraviolet, and then X-rays, and then gamma rays, huh? Pretty amazing. And look, it's all connected. From radio waves to gamma rays to visible light in between, it's all frequencies of electromagnetic radiation. How is this staying up? So everything outside of the visible spectrum is invisible, right? Wrong! Ha-ha! Bam! Huh?
That is an X-ray, a picture we can take using this part of the spectrum.
We can use special cameras to see outside of the visible spectrum. Huh? Huh? Right? Yeah. Okay, you got it. Huh? And look at these. These are night vision goggles. They help you see in the dark. They use part of the spectrum called infrared.
For those of you keeping score, that's this part of the spectrum right here.
Pretty neat, right? I would sell you these, but they're already spoken for. Oh, and here he comes now.
Hey, Sal.
Hey, how you doing?
You got those goggles I ordered?
Yeah, go ahead, help yourself.
Thanks for putting them aside. Can I put them on my tab?
Yeah, no problem.
All right, thanks, Sal.
Okay, see you later. Nice kid. He's always in a rush, though.
Phil, is that you?
Yeah,
Do you need the flashlight?
I don't. Turn it off. I could totally make my way over to you. Oh.
I can hear you.
Yeah, I'm right here.
Oh.
Right here.
Hi.
Because I have night vision goggles. Ooh, check it out.
Oh, cool.
Pretty cool, right?
That's awesome.
So here's the spectrum again, and here's visible light. My night vision goggles use infrared, this part of the spectrum here with wavelengths just a little bit longer than the red we can see.
Outside of the visible light spectrum.
All right, I would say that's allowed.
No visible light, and I will see the next ball. Have you got it set up?
I set it up while you were out.
Okay, good. I'm gonna sit in the chair and see if I can see it. Okay, here we go. Oh wow, I can totally see everything.
Can you tell me what the ball says?
It says you win.
Nicely done.
So let's recap. This challenge is the same as the last challenge. The light from the ball was magnified by the lens, sent around a corner by reflecting it off a mirror, and flipped back around by using another mirror. But this time it's dark. So, using infrared light, thanks to my night vision goggles, I was able to see the ball and win the game.
The light manipulation challenge is done. Science Max experiments at large. Time to turn the lights back on.
Yep, absolutely.
Huh.
What did you do back there?
I guess we blew a fuse or something.
Uh-oh.
Science Max! What good is science if you can't use it to give you super strength? Well, I try to do just that on this episode of Science Max. Lifting more, rolling more, and a whole lot of running. Simple machines. Today on Science Max, experiments at large. Greetings, Science Maximites. I have a question for you. Have you ever wanted superpowers? Like super strength? Well, today on Science Max Experiments at Large, I'm gonna give you and myself super strength using the power of science. But we're gonna do things a little differently today. You see, well, the portal hasn't been working perfectly since I built it. But I ordered a new particle impulse controller, and all I have to do is get it back to the lab. Perfect timing. It looks like the portal is broken. Okay, well, no problem.
Okay, I'm here. Wow.
That's perfect. One particle impulse controller for you.
All right, thanks very much.
No problem.
Appreciate it.
Enjoy.
Thank you. Well, my very own particle impulse controller, okay. That's as heavy as I thought it was gonna be. All right, Science Maximites, this episode of Science Max Experiments at Large is gonna be a little different because today I'm not gonna have an expert come and help me because I'm gonna move that giant, heavy particle impulse controller all the way across the parking lot and all the way up that loading ramp by myself with nobody's help. How am I gonna move a giant, heavy machine all that way if I can barely even budget? Well, I'm gonna give myself superpowers, super strength with the power of simple machines. And the first machine we're gonna start with is the lever, which I guess I should go back to the lab to tell you about. All right, Sal, I'll see you next time. Oh, hey, how you doing? Let me guess, you got some work to do and you need it done easy, right? I mean, look at this book. I mean, you could pick it up, but what, are you gonna be some sort of book picker-upper person now? Is that all you're gonna do? Is that gonna be your life, just picking up books left, right, and center? No, you're smarter than that. You know what you need? A lever, like this. Now, I know what you're thinking. I know you're thinking, hey, this is just a plank. You're right. That's because you're smart. A plank can be a lever. All you need is two sides and a place for it to pivot. A fulcrum. It can be anything. Look at this. Bam! Now it's pivoting. I put the book on this side, and then I push down on that side. I'm doing work
easy. Hey, look at me doing this work over here. If I want to do more work, I could move the fulcrum a little bit further over. Now I do lots of work, but I lift the book a lot further. Look at that. Whoa, wow, whoa, yeah. Huh? What do you say? What do you say, huh? Huh? You don't like this lever? Don't worry. Hold on, I got another one for you here. Hey, take this stick. All you need is 2 ends and a place for it to pivot, like this. Bam. Now, it's a lever. This side goes down, that side goes up. Down, up. It's a lever. It's a lever. You want to make a catapult? Use a spoon. The place where the spoon pivots is the fulcrum. And now, it's a lever. It's a lever. It's a lever. Look at this lamp. Now, it's a lever. Scissors, 2 levers. Your forearm, it's a lever, 2 ends, and the fulcrum where it pivots, yeah, the fulcrum can be at one end. Crazy. This fish, you guessed it, now it's a lever. And now you know your levers. Okay, where were we? Oh yeah, levers. So you can use levers to become much stronger, or at least lift something you couldn't normally lift. Levers are simple machines and they work like this. Levers are just a long rod or a stick or pole or a piece of wood like I've got here, and something for them to pivot on, a fulcrum. Now let's say you have something heavy, like this book. Sure, I can lift it, but what if I told you I can lift this heavy book with this book? Now, if the fulcrum is in the middle, like a seesaw, you can tell that book is much heavier than the other book. But watch what happens when I move the fulcrum. Huh? It's like magic, but it's not magic, it's science. Whoa. It's because the small weight is moving a long distance and the heavy weight is moving a short distance. Small weight, long distance, heavy weight, short distance. So, everything balances out. But here's where it gets interesting. The longer your lever, the more weight you can lift. These are 2 heavy cinder blocks. There's the fulcrum, and here is a very long lever with which I am going to lift those cinder blocks with this book. Ha-ha! And there you have it, levers. Now, back to the particle impulse controller. Oh, right.
Ha 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 ha! Lever! Here we go. I got my giant lever. The bigger the lever is, the easier it is to do the work. I need a fulcrum. Just about anything will do for a fulcrum. And put that there. Now the hardest part is getting it on the lever. Okay. All right, hardest part is over. Get the lever up on the fulcrum. And, oh, look at this. No problem, 1 finger lifting. It suddenly became very easy for me to move this. I guess I need to do more than just lift it though, huh? Because I have to move it all the way. Oh, rollers! Come on, back to the lab.
Okay, rollers. Rollers are like wheels, except they're not attached to anything. In ancient times, they used to move giant, heavy blocks of stone using rollers. We can demonstrate using a book. Now get a book, put it on a table, and try to move it across the table. You'll see that it's very difficult. I can't move this book across the table. I can't. Okay, it's not really that hard, but still, it takes effort. But if we get some rollers, I like to use pencil crayons and not pencils, and here's why. Take a closer look. You see, pencils aren't round. They're hexagonal. They have 6 sides, whereas pencil crayons are round. And of course, if you want something to roll, you want something round. So get a bunch of pencil crayons and put them on the table and put the book on the pencil crayons, and you'll see that suddenly moving it is a lot easier. All right, that's rollers. Back I go. time for science so simple a caveman could do it. This is a caveman. This is a rock.
Knock!
It is a well-known scientific fact that if this caveman were to try to move that rock, he would not know how to do it easily. Poor caveman. But in ancient times, people learned how to move heavy rocks using ropes
No!
and rollers.
Oh, wrong Earth.
Yes, rollers.
Wrong Earth.
Rollers.
Wrong Earth.
Close enough. Rollers make it much easier to move a heavy object. But they aren't perfect. So the wheel was invented. The wheel is a simple machine and one of mankind's greatest inventions. But no, that's not how it works.
No?
Wheels go on axles, which go under a platform. Now you have something to place that heavy rock on to move it around. But all these great inventions came after the time of the caveman. Cavemen had to do everything the hard way. Join us next time for more science.
Okay, I've got rollers. They're just plastic pipes, but they'll work perfectly. I put them here. And now to lift up the machine. Okay. Perfect. And so the rollers go underneath like that. And then whoa. Whoa, careful. Look at that. No problem. Wait, I gotta get rid of this to get it moving. Now, the trick with rollers is you have to keep taking them out of the back and putting them in the front. But, whoa. It's stop, rollers, stop. Oh no. Okay, whoa, rollers, easy. There we go. Okay, in the front, roll it forward.
Now I know what you're thinking. You're thinking this seems like a lot of work. And it's true, moving the rollers back and forth does take some time. But did you know this was how the pyramids were built? It's true. Giant stone blocks were moved on rollers just like I'm doing here. And as you can see, what worked for the ancient Egyptians works for me too. Uh-oh. Yeah, there's a hill here. If I go down the hill, it's gonna start rolling faster than I can do the rollers. I'm gonna need some help. Oh, I know! Pulleys! Okay, pulleys. Pulleys are a great way to change the direction of force. I've got a rope going through this pulley and down to a book, so when I pull the rope down, the book goes up. Changing the direction of force can be very helpful, but pulleys can be helpful in another way. Pulleys can let you lift something that you couldn't normally lift. Now the rope goes up and down and up and down and up and down. And the force I need to lift this cinder block is a lot less than if I was just lifting it by myself. But I've got to pull a lot more rope. That's called mechanical advantage. Spreading out the force
over a longer pull so you can lift a larger weight. If you use more pulleys, it reduces the amount of force. 1 pulley, same amount. 2 pulleys, half the force. 3 pulleys, 1/3. So I've got 5 pulleys here, which means I only need 1/5 the force to lift this cinder block. So there you go, pulleys. Now back to the, wait a minute. This calls for a mini-max. So how much weight can you lift with pulleys? Well, as much as you want, really. I have 4 pulleys on the bottom and 4 pulleys at the top. That means with 8 pulleys, I only have to lift 1/8 of my weight plus the weight of the chair I'm sitting in. And if I keep pulling, you will see that the chair I'm sitting in is roped to the pulleys. So now we see if I can pull myself up with nothing but pulleys. Look at that! I'm totally lifting myself into the air with the power of pulleys. And I don't need to use 2 hands. In fact, I only need to use 1 finger to hold myself up. And my thumb, obviously, to hold the rope. That is the power of pulleys. I can almost make myself fly. Well, almost. Now, back to the particle impulse controller. Letting myself down. Whoop. Whoop, whoop, whoop. Particle impulse controller. Let's go. Wait. All right, I've been able to use this pulley to lower it down the hill at the speed I want to go. Interestingly, I'm using the pulley not to make it lighter, but to just change the direction of force. And I managed to get it right here at the bottom. Now I've got to get it up onto the loading dock, so I think this is where I need a ramp. Whoa, whoa, oh. Here is something mind-bending you can do with pulleys. These buckets are attached to the table through a pulley. There's nothing holding this table up except for the weight of the buckets pushing down on the table. So if I took the buckets off the table, the weight of the buckets pulls the table up. But because the buckets are on the table, everything is in balance. Mind-bending, right? Okay, wait, it gets better. If I took a weight and I put it on the table, the weight of the buckets isn't enough to keep the table up. So I have to add more weight to the buckets so the buckets pull the table up. Whoa. And there you have it. It's weird, it's mind-bending, it's science. Okay. Ramps. Ramps are a great way to move something up. I will demonstrate using, you guessed it, a book. Let's say I wanted to move this heavy book on top of this stack of books using just this little string. Watch what happens. The string breaks, but if I built a ramp to get the book on top of this stack, and I use the same kind of string, watch what happens this time. Whoa. You see, the ramp distributes the force, so you use less force to pull the book over the same amount of distance, and I can get it up to the top of the stack of books, and the string doesn't break. So ramps,
Let's put him into action. Woo. My simple machines have worked great. I've managed to get the particle impulse controller all the way to the loading dock. But now it's time for the hardest job. What I need to do is build a ramp that goes from the ground up to the loading dock. Then I need to pull the heavy impulse controller up the ramp. The best way to do that is to use a system of pulleys. I have 3 pulleys on one end and 2 pulleys on the controller. Because I have 5 pulleys working together, I'll only have to lift 1/5 of the weight. The plan is to get it tipped over onto the ramp, then use rollers to help it roll up as I pull on the rope. There's 3 pulleys on that piece of wood over there, and I got 2 pulleys on this piece of wood here. And now, if I pull, and I carefully put the rollers underneath, careful, careful. Perfect! Okay, now it's on the rollers, and now I can pull it up the ramp. Now, I gotta carefully put new rollers underneath as I go. Pull it up the ramp. Roller. I know what you're thinking. It still seems pretty difficult. If only the simple machines could give me longer arms. Well, they can't do that. But what they can do is give me the strength to do this heavy job with no one else around but me. Hopefully that won't be a problem. There we go! I did it! All the way across the parking lot and up onto the loading dock with the help of levers, rollers, ramps, and pulleys. The hard part's done. Now I just have to get it into the lab. All right, let's see if all that effort was worth it. I think it's working! Well, there you go. Thanks very much for joining me on Science Max Experiments at Large. I think I'm gonna go home because it's been a long day and I could really use the rest. See you next time. Wait, I hit 3, 4, 1, 2. I should have hit 3, 4, 2, 1. Yeah, that's okay. I'll just go back and, Science Max! Today on Science Max, we're using the force, says. Pendulums are pretty simple. It swings back and forth. Marbles, dominoes, sledgehammer, trebuchet, rockets, levers, rockets, tension, and that's just the main experiment.
Maxed out dominoes.
I love that idea.
All this and more on this episode of Science Max Experiments at Large. Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. Today, we're going to be looking at air pressure and friction and simple machines like levers, pulleys, and gears. We're going to look at some rotational energy, some spring tension, and gravity. We need all those things because we're building Rube Goldberg machines! Rube Goldberg machines! Rube Goldberg machines! Rube Goldberg machines! Rube Goldberg, you heard me say Rube Goldberg machine? Okay, we got that part? Okay, good. Rube Goldberg was a cartoonist who came up with the idea of having a simple task done by a machine that was extremely complicated. There are Rube Goldberg competitions all over the world, and there's only a few rules. First, a human can only touch it once by starting the whole thing off, and then the machine has to work all on its own. I know what you're thinking. You're thinking, Phil, what's the science behind a Rube Goldberg machine? Well, it's all about changing energy. Remember, you start the whole thing off with just a little push. But if you want the machine to keep going and going and going, you have to come up with clever ways to add more energy to the system so you've got more energy to keep the machine going. So check this out. A bunch of stacked dominoes, which will start a chain reaction that leads to this mouse trap, which has all of its energy stored in the spring tension, which will release the ball. Boing! Check this one out.
It's a bunch of pulleys, and there's a rope that goes up and down and up, attached to this lever where there's a ball, and there's a big heavy weight here. And when the weight gets knocked off the table, the ball falls into the hole and then goes down the tube, and so on. Check this one out. Here's a great way to change the direction of something. Say the ball falls on this lever. Well, it's weighted on this end, but then the weight falls off and the ball goes this way. And, the portal turned on. I gotta pick an expert. Okay, hold on a second. 10 seconds before the portal resets. Sonia from the Ontario Science Center. Perfect. And there we go. Tons of time. 3, 2, 1. Sonia!
Hey.
I portaled in 3 blocks away. I had to run here.
Okay. You're here now?
Yeah, I didn't put the coordinates in when I left. Anyway.
It's okay. Breathe.
Sonia from the Ontario Science Center. I'm glad you're here because we are gonna build a Rube Goldberg machine.
Really?
Yeah.
Oh my gosh, I'm so excited.
Yeah?
Yes.
I'm so excited too. Check it out. This giant room. I've never done anything with it, so why don't we build a giant machine in here?
Why not?
Okay, so here's the rules. The Rube Goldberg machine has to start with one simple thing, right?
Yep.
So we're gonna start with this marble, and we send it on its way, and then a whole bunch of stuff happens, and at the end, we press that button.
That button?
Yeah.
What does it do?
I've never used it before, but when we hit that button, we get cake.
Cake?
A cake will portal in, and we'll have cake.
Oh my goodness, can we get chocolate cake?
We can totally have chocolate cake.
All right, now I'm really, really excited.
Okay, so can I start?
Absolutely.
Great, because I saw some stuff over here.
Okay.
This is a pendulum. It's a weight that swings. It swings back and forth. Pendulums are pretty simple. It swings back and forth. Predicting the path of a pendulum, pretty simple. It's gonna swing back and forth. But wait, as I make it so much more complex by adding a pendulum. Now I've got a pendulum down here, and that one swings back and forth, and I've got a pendulum up here that swings back and forth. What will happen to this part of the pendulum when I let it go? Can you predict? Let's find out. This is a double pendulum, and predicting the path of a double pendulum is really difficult. It's still simple physics, but because there's a moving part attached to a moving part, it makes it way more complex. So, the question is, can we max it out even more? Of course we can. These are chaos pendulums. This one's a lever, and it's got another lever on the end. Whoa, and this one here is a perfectly balanced lever, and it's got a pendulum on either side. Whoa. Whoa. Scientists and engineers have always said that the more moving parts something has, the more complex they are. Science. Sonia and I are taking turns building our Rube Goldberg machine. The first section was my turn, and I explained it to Sonia. Right here, we have what is known as a ramp. Ooh, yeah, I know you know.
Fancy.
Right, so we put a marble on the ramp that rolls along this thing into what is known as a pylon. And then we've got these guys right here, which are dominoes. And when that falls off the table, it'll pull on the string, and then it's attached to this. Now, this is the release mechanism, so when that string gets pulled, it will let go, and it will fire this, which is a trebuchet.
All right, should we test it out?
Absolutely. You
Can
want
I
to try
try
it?
it?
Yeah, please.
Yeah.
Okay.
Okay, 3, 2, 1. Huh.
Wait.
Didn't go. Why didn't?
Well, the domino doesn't seem to be heavy enough to make this contraption fire.
You know what, Phil?
What?
I have an idea.
Oh, yeah?
Maxed out dominoes.
Maxed out dominoes. I love that idea. Why are they maxed out? Do they glow in the dark?
We'll see.
Do they produce electricity?
We'll see.
Do they talk to animals?
We will
Do they
see.
dissolve in water? Whoa, maxed out dominoes.
That's what I'm talking about.
These are very maxed out. Okay,
So
so
we
now.
started off with this domino.
Uh-huh.
Then we went bigger.
Yeah.
Bigger,
Yeah.
bigger, 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 bigger. And we went to the biggest.
Right.
And this is where we're gonna get the most weight, which is gonna trigger it and release.
Ha ha! Woo-hoo. Here we go. 3, 2, 1.
Here we go.
The one thing to remember about Rube Goldberg machines is they never work perfectly every time.
Didn't go.
But we tweaked it and adjusted things, and then...
Here we go.
3, 2, 1. Whoa!
Nice.
this out. Whoop. Okay, so
Nice.
now that we've got the trebuchet firing,
Yep.
and the ball is going over there, we need to get the ball going over here
Yeah.
to
The
cake button.
cake button.
I can't wait for the cake. So I have an idea. Come on.
Okay.
No, wait. Changing direction stuff is over.
Okay.
Now we're gonna talk about tension. What's tension? One more than nine shin. Get it? Because tension and that's, okay, tension is the force that we usually talk about when we think about pulling a rope or a chain or something like that, because you know the old expression, you can't push a rope. But today we are gonna push a rope. I have a rope right here, and I'm going to push it using another force called flexion. I've got some pieces of plastic here, and they bend or flex. And when they do, they want to spring back. But I'm gonna prevent them from springing back by putting them in between these knots. And look, the rope now stays up. And I take another piece, and I stick it on this knot, and then I bend it all the way. This is not terrifying. Really, it's not terrifying at all. Okay, good. And then I take this piece, and I put it here, and I bend it around, and so now we have a rope that's being pushed, and we're defying gravity, and we're making a cool art sculpture. All right, one more here. Ooh, okay, here we go. And flexing. And whoa. Ha-ha! There you go. I've pushed a rope, defied gravity, and made a cool art sculpture. Okay, well, I guess technically I haven't really pushed the rope because we're still pulling from each knot. And I guess I haven't really defied gravity because that one's sitting on the table and all the others are sitting on top of that. But you can't argue that I made a cool art sculpture. Ha-ha! Art! I mean, science. Sonia and I are maxing out a Rube Goldberg machine. The first part worked pretty well, and now we need to change the ball's direction. So it's trebuchet. Trebuchet fires the ball, right?
Yeah.
Right now I want to tell you the story of the ball. First, it goes through this fancy film of tin foil.
Aluminum foil?
Right, aluminum foil, because it's, yeah, you're right, it's made of aluminum. It enters this large receptacle.
A garbage can?
You also could be called a garbage can. It falls into this conular device.
Funnel?
A funnel, yes, you could call it a funnel. And then it enters the change-o-direction-o-matic, which is a lever. There's a weight on that end, then it falls off, then the ball goes this way.
Phil?
Or that way. The one thing you need most of all when making a Rube Goldberg machine is patience. Ball goes in the funnel, knocks that off, changes direction, and then it goes this way.
Okay.
And that's all I got so far.
So, not bad.
Yeah.
But we really want to get closer to that way.
Right, because that's the button that gives us cake.
How about we use some chemical energy for this?
Ooh, chemical energy.
I have an idea for this one. Let me go get it.
Go for it.
This is my idea.
Okay.
Ball's actually gonna roll down the tube.
Oh yeah, because this is a rat trap, right?
Yeah.
Which is like bigger than a mouse trap.
And then it's gonna hit it. Yeah. Nice.
Ooh, so this flips around.
Exactly.
And what's this?
That is something called an antacid tablet. Some water.
And the antacid and the water react. Oh!
It blew. Do you want to test it out?
Sure, can I?
Okay.
Okay, ball comes through this, goes down there, comes out of this, and on the ramp.
Onto the trap.
Oh.
And
So then
Nice.
it fires up
Yep.
and hits something else
Yeah.
and something button cake. So we got a lot of different energies, but you know what one we're missing?
What?
Is electrical energy.
yeah, you're actually right.
I've got a great idea. Hold on.
All right. Let's see what he comes up with.
This is a chain of beads, and this is glass. Now, if I was to drop the chain of beads, what will happen? It will fall. Yes, that's right. It'll fall because of gravity. But watch this. This side goes up. Why? Because of gravity. Wait a minute. Why does one side go up because of gravity?
Well, it gets a little complicated, but I can explain. But I think I'll have to put the beads back in the glass. Okay, so what's going on? Well, when this part of the chain starts falling out, it gets longer and longer, and it has more mass than this side of the chain. And if it has more mass, then it has more inertia. And when it starts yanking out very hard, this side of the chain gets yanked up out of the glass very quickly. When it gets yanked up hard, it flies into the air. But then, of course, the direction has to change, so it goes around a curve and then goes back down. Because of the speed that it's going, that curve starts lifting up over the top of the glass. And that's how it works. There's a big difference in energy because this chain falls far. I try it from here, and it doesn't work as well. Why? Because the drop from here to here isn't as big. You want lots of force acting on the falling chain, which means the higher you do it from, the better it works. So maybe we should max it out. Yeah. But wait, we should wait for it to stop. And now let's max it out. This is a really long chain, and this is a really long drop. Let's see what happens. Whoa! Look at that! Whoa! Super maxed out! Science! Sonia and I have used potential energy, the lever, and chemical energy. But you know what one we're missing?
What?
Is electrical energy. Electromagnetism. So watch. The chemical rockets, which we've had from before, they'll fire up, they'll hit the underside of this tray. The marbles will fall and flick this switch. See that sledgehammer?
Uh-huh.
This is an electromagnet, and it will attract the metal in the sledgehammer. Watch this, ready?
There.
There. Magnetized, electromagnetism. Now, when the marbles fall, it'll turn the electromagnet off, and the hammer will fall.
Oh, that's pretty cool, actually.
Right?
Can we
So
try it?
let's try it. Here's something we didn't know. Predicting the flight path of an antacid rocket canister is almost impossible. We had them aim the same way every time. But we stuck with it, and being patient is key, and eventually it worked. The chemical rockets fire, and they hit the tray. All right!
That's pretty cool.
Yeah, so now we just need hammer hit something, and then something, 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 button, cake.
I have an idea.
All right. Cake, any minute now. This is a basketball. It bounces. This is a golf ball. It bounces. But it never bounces as high as where I dropped it from. But watch as I put the golf ball on top of the basketball. Whoa! Why does the golf ball bounce higher than where I dropped it from? How is this possible? I only bounced the golf ball from 1 meter high. So what's going on? Well, as the basketball hits the ground, it compresses, storing the potential energy of its bounce, about to give that energy back as it bounces up again. But this energy works as a springboard for the golf ball. And since the golf ball has a lot less mass than the basketball, the upwards kinetic energy of the basketball is given to the golf ball. So, let's max it out. Ball, on a ball, on a ball. 3-ball bounce. Oh, did you see that? Ball, on a ball, on a ball, on a ball. Quadruple ball bounce. Oh, oh. Oh. No, wait. Turns out getting 4 balls to drop straight down on top of each other is pretty difficult. So, we know the mass of the ball is important. Why don't we max it out in a different way? This is a Swiss ball for exercising. It has a lot more mass than a golf ball. So, let's try it out. There you go. The transfer of energy between balls. A great way to lose golf balls. Sonia has added one more step to our Rube Goldberg machine, a stomp rocket. It's a hammer rocket.
Exactly.
I like
So
that.
what's gonna happen is the hammer is gonna hit our bottle, which
Right.
is gonna release all that air that's built up inside of it. It's gonna hit that button,
Wait. The rocket hits the button.
and then we get some
Cake!
cake.
Cake! Oh, so this is it. So we're done the Rube Goldberg machine with this last step.
Okay.
Do you want to do it?
I think we should do it.
Ready?
Ready?
3, 2, 1. Let's pause here just before the cake portal's in and recap the science. A marble on top of this ramp has potential energy. As it rolls down, that changes to kinetic energy, which transfers to some stacked dominoes. They fall in a chain reaction, finally causing bigger and bigger dominoes to fall, giving the last domino enough mass to pull a string, attached through some pulleys, to a quick release on a trebuchet. Now, a trebuchet is a first-class lever with a weight on one side and a sling and a ball on the other. If the weight falls, the sling releases the ball at the right moment and it sails through the air. It's caught in a garbage can and changes directions on a few ramps and another lever as a teeter-totter. Finally, it falls onto a rat trap, which has more energy stored in the tension of the spring. The rat trap smacks another lever, which flips around, turning over some antacid rockets. This allows the antacid to mix with the water and start a chemical reaction that produces carbon dioxide, which eventually builds up enough pressure to fire the container to another lever, which tips, dropping some marbles on a string attached to a switch. That turns off the electricity to our electromagnet. And when an electromagnet doesn't have electricity, it stops being a magnet. So our sledgehammer starts to fall. Now, our sledgehammer is heavy, so it has both mass and speed when it hits this plastic bottle. All that inertia crushes the bottle, reducing its volume. The air gets put under pressure and pushes out through a tube, which takes our stomp rocket with it. The stomp rocket flies through the air and hits our cake button, which then portals in some cake. Guess we really didn't think that through, huh? The cake should have landed on a table or something.
Would have been nice.
There you go, Science Max Experiments at Large, Rube Goldberg machine. Are you sure you don't want some of this cake?
No, let's
But,
let's go.
uh,